In the northern part of Chile, there is a place where the Earth's atmosphere almost surrenders to the sky. At 3,046 meters above sea level, the air is so dry that skin cracks within hours and moisture evaporates before it settles on the stone. It almost never rains here, some years not a drop at all. This peak is called Cerro Armazones, and it is here that humanity is building the largest optical telescope that has ever existed. The European Southern Observatory, ESO, blasted the first rocks on the mountainside back in 2014, clearing the area for the foundation. Before even a single bolt could be inserted, the builders had to cut away the very top of the mountain, removing the top 18,000 tons of rock to create a flat platform capable of supporting a structure weighing several thousand tons without the slightest tilt. This was not a symbolic gesture, it was an engineering necessity because the telescope being built here does not allow even a millimeter of deviation from the design geometry. Its name is the Extremely Large Telescope, ELT. Its primary mirror has a has a diameter of 39.3 meters. Not just a record, but a quantum leap ahead of any previous instrument. For comparison, the largest optical telescope currently in operation, the Gran Telescopio Canarias in the Canary Islands, has a mirror measuring 10.4 meters. The ELT is almost 4 times wider in diameter, meaning it collects about 15 times more light per unit of observation time. The light beam that the telescope operates on is not an abstraction, it is real photons, real information, traveling for billions of years through the void of space to end its journey on this mountain in Chile. The ELT's light collecting surface area exceeds the combined area of all large optical telescopes built before 2000. This is not a metaphor for superiority. It is a physical reality that cannot be circumvented by any software solutions or space basing. Light is everything, and the ELT collects more light than any telescope before it. When the Hubble Space Telescope launched into space in April 1990, astronomy experienced a revolution that is difficult to overstate. For the first time, an optical instrument has emerged above the atmosphere. That is invisible, shimmering veil of air that blurs starlight and limits the resolution of any ground-based telescope by a fundamental physical barrier. During its 35 years of operation, Hubble has transmitted more than 1 million images to Earth, resulting in more than 21,000 scientific publications in peer-reviewed journals, a record unmatched by any other observatory in history. He showed us the pillars of creation in the Eagle Nebula, galaxy collisions hundreds of millions of light years away, and the ultra-deep field, a patch of sky the size of a pea held at arm's length that has yielded some 10,000 galaxies, each a universe of stars. But Hubble has a fundamental limitation that cannot be removed by a software update or a camera replacement. Its 2.4 meter diameter mirror is too small to capture enough light from the atmospheres of distant rocky planets and resolve that light into a spectrum with sufficient resolution for chemical analysis. On December 25, 2021, the James Webb Space Telescope, JWST, launched into space. It has a 6.5 meter mirror, operates in the infrared range, and is capable of peering into the universe's past 13.4 billion years ago. Webb revolutionized our understanding of the early universe. In March 2023, a team led by Dr. Ivo Labbé of Swinburne University announced the discovery of 6 massive galaxies that existed just 500 to 700 million years after the Big Bang. Their mass turned out to be so high that it contradicted standard cosmological models, and the team recalculated the results 3 times, convinced of an error, but the data gave the same answer each time. However, even Webb can't do what ELTs are built to do. Direct spectroscopy of the atmospheres of small rocky planets in the habitable zones of solar-type stars remains beyond the capabilities of the 6-meter mirror. The signal is too weak, the noise is too high. The resolution is 16 times greater than Hubble's. And that's not just better pictures, it's a fundamentally different ability to extract information from the faintest streams of light in the universe. To understand why mirror size is so important, we need to understand how astronomers read the composition of other worlds' atmospheres. The method is called transit spectroscopy, and it is based on a phenomenon that any schoolchild has observed in a physics lab. Different substances absorb light at different wavelengths. When a planet passes in front of its star, a small portion of the starlight passes through the planet's atmosphere tangentially to its surface. Molecules in this atmosphere absorb specific wavelengths, while constant wavelengths. Oxygen leaves a signature at 769 nanometers. Water vapor in the near infrared, and carbon dioxide and methane at their own frequencies. If a telescope captures this radiation, weakened by the stellar passage, and breaks it down into a spectrum, the chemical fingerprint of the atmosphere becomes visible, like a barcode encoded in the color of the fading light. Hubble and Webb have already used this method on gas giants, where the atmosphere is huge and the signal is strong enough for existing mirrors. In September 2022, Webb detected carbon dioxide in the atmosphere of the exoplanet WASP-39b, a hot gas giant with an orbital period of 4 days and a mass 11 times that of Earth. It was a triumph. The first definitive detection of CO2 in the atmosphere of a planet outside the solar system, published in Nature in November 2022 by a team of more than 300 authors. But WASP-39b is not a place for life in any conceivable sense, a red-hot ball of gas whose surface is hotter than a blast furnace. The real target is a rocky planet roughly the size of Earth, orbiting in the habitable zone of its star, where liquid water is possible, with oxygen and water vapor in the spectrum of its atmosphere. Such a detection requires tens of times more light than Webb collects, because the atmosphere of a small, rocky planet produces a signal thousands of times weaker than the atmosphere of a puffy, hot giant. The luminous flux scales as the square of the mirror diameter. The ratio of the ELT's mirror areas to Webb's is 39.3 over 6.5 squared. That's about 36. The ELT collects 36 times more photons per second than humanity's most advanced space telescope. 36 isn't an improvement, it's a change of era. The ELT dome rises 74 meters, the height of a 22-story building, and is designed to rotate with the sky on steel rails with the precision of fractions of an arc-second, opening and closing in a matter of minutes. The dome weighs approximately 6,100 tons and must move without vibrations that could disrupt the alignment of the mirror segments inside. The telescopic mount itself, the mechanical structure that holds the mirrors, weighs about 3,000 tons and must be aimed and held with precision, measured in fractions of an arc-second. 1 arc-second is 1/3,600th of a degree, the angle subtended by a 2.5 centimeter coin seen from 5 kilometers away. The ELT is more precise than that. Each of the 798 hexagonal segments of the primary mirror, 1.4 meters in diameter, rest on 3 motorized actuators, capable of adjusting its position up to 1,000 times per second. It's called adaptive optics, and ELT is applying it on a scale that has never been attempted before. The system uses a laser guide star. A powerful laser beam is fired into the sky and excites sodium atoms in the upper atmosphere at an altitude of about 90 kilometers, creating a bright artificial spot. The control system measures how this spot is distorted by atmospheric turbulence on its way down to the telescope's mirror and builds a map of the flickering in real time, compensating for it in the fractions of a second before the light reaches the detector. As a result, the ground-based telescope produces images that are not only comparable in sharpness to the Hubble Space Telescope in space, they surpass it because a mirror 16 times larger in diameter concentrates light into a point with an angular resolution unachievable with a 2.4 meter instrument. ESO has already tested these principles on the operating VLT telescopes at Paranal, the closest operating observatory 25 kilometers from the ELT construction site, and the results confirm that the technology works. The main ELT mirror is not made in one place or by one company. The 798 segments are produced in a coordinated industrial chain spanning several European countries. And this in itself is an unprecedented logistical achievement. Each segment starts out as a blank of a special glass ceramic called Zerodar. manufactured by Schott in Mainz, Germany, a material whose coefficient of thermal expansion is close to zero. On a mountain where the temperature drops to zero at night and rises to 20 degrees above zero during the day, a mirror that changes shape when heated would make all images blurry. Zero maintains geometry. The segment polishing is being carried out by a consortium led by REOSC in France, a subsidiary of the aerospace holding Safran, with the involvement of partners from other European countries. It takes approximately 3 months of continuous work to polish one segment, and the target surface accuracy is less than 7 nanometers of standard deviation over the entire area of the front face, with a diameter of 1.4 meters. 7 nanometers is less than the diameter of 10 DNA molecules laid side by side. This means processing glass plates 1.5 square meters in area, with a precision exceeding the capabilities of most metrology instruments just 20 years ago. After polishing, each segment is coated with a reflective layer, silver or aluminum, and undergoes interferometric testing, in which laser interference patterns verify the surface's compliance with specifications with an accuracy of nanometers. All 798 segments must pass through this conveyor belt. Preparation, polishing, testing, coating, final inspection, transportation to Chile, installation, and ultimately function as a single mirror with a diameter of almost 40 meters. A segmented mirror faces a problem that a monolithic mirror does not. All 798 fragments must be in phase, that is, aligned to within fractions of a wavelength of visible light to act as a single continuous reflective surface. If even a few segments are misaligned by more than a few tens of nanometers, the telescope's angular resolution degrades, and the whole point of the giant mirror is lost. To address this challenge, SO developed the Active Phasing and Alignment System, APAS, which uses wave sensors distributed along the telescope's optical path to continuously measure alignment quality and send correction signals to actuators in each segment. The initial alignment, aligning all segments from scratch after the last one that is installed, will take, according to engineers' calculations, several weeks of intensive work with iterative measurements and corrections until the telescope achieves full coherence. Even after first light in 2028, the telescope will not immediately reach its design capacity. Commissioning such an instrument is a process of months and years of sequential calibration, eliminating systematic errors and launching instruments one after another. But even in partially calibrated mode with a reduced performance, the ELT load will do science that no existing telescope can do, simply because its 39-meter diameter leaves no other option. On August 24, 2016, one of the most explosive news stories in the history of astrophysics occurred. An international team led by Guillaume Anglada Escude of Queen Mary, University of London, announced the discovery of a planet orbiting the star closest to the Sun. The planet was designated Proxima Centauri b. Its mass is at least 1.27 times that of Earth. Its orbit is in the habitable zone of Proxima Centauri. Its distance from us is 4.24 light years, and it makes a complete revolution around the star in 11.2 Earth days. It's the closest exoplanet we know of, and it's potentially habitable. But Proxima Centauri is a red dwarf, which poses a problem. In March 2019, researchers analyzing data from the Everscope telescope array detected a superflare from Proxima Centauri, a burst of ultraviolet and X-ray radiation approximately 100 times more powerful than any flare ever recorded from our Sun. Such events could gradually strip away the atmosphere from a planet lacking a strong enough magnetic field to protect it, leaving the question of whether Proxima b retains its atmosphere unknown. ELT can answer this question within the first years of work. 40 light years away in the constellation Aquarius lies the star system of TRAPPIST-1, a dim red dwarf that in February 2017 became perhaps the most famous object of modern exoplanetary science. On February 23, 2017, a team led by Michael Gillen of the University of Liège published a discovery in Nature. TRAPPIST-1 is orbited by 7 Earth-sized planets, 3 of which, A, F, and G, are in the star's habitable zone, where liquid water is theoretically possible. Not just one potentially habitable planet, but 3 in one system, at a distance easily observable by modern telescopes, with a star so small that its transits give a relatively powerful signal relative to the stellar disk. Webb Hutchin has already begun working with this system. In 2023, teams analyzed the thermal radiation from TRAPPIST-1c and concluded that the planet likely lacks a dense atmosphere. Its surface behaves like the bare rock. But TRAPPIST-1e, F, and G, the habitable zone planets, are awaiting a more powerful instrument. The signal from their atmospheres is at the limit of Webb's 6-meter mirror and requires a 36-fold amplification. It is precisely this amplification that the ELT mirror will provide. Teams from the University of Bern and the University of Leuven have already published calculations showing that the ELT with the Harmony instrument is capable of detecting oxygen absorption in the atmosphere of TRAPPIST-1e if its concentration is comparable to that of Earth, within a realistic number of transit observations. This isn't some hypothetical future beyond our lifetime. With first light in 2028 and full power by 2030, the answer could come as early as 2031 to 2033, given a lucky combination of circumstances and a sufficiently stable atmosphere above Cerro Armazones. In April 2017, Jason Dittman and colleagues at the Harvard-Smithsonian Center for Astrophysics announced the discovery of LHS 114-OB, a super-Earth with a mass of about 6.6 Earth masses orbiting in the habitable zone of the red dwarf star LHS 114-O, 39 light-years away in the constellation Cetus. This planet is particularly interesting because its host star is calmer than Proxima Centauri, and TRAPPIST-1. It has fewer flares, a less extreme ultraviolet radiation, and a better chance of retaining its atmosphere. In 2023, an updated analysis of Webb's data allowed a team led by Charles Quintana to provide a new estimate of the mass and radius of LHS 114-OB. Parameters suggest that it may be a water world, a planet with a thick ice layer or deep ocean beneath a thin atmosphere. If there's an atmosphere there, the ELT will read its composition, and this will not be an indirect inference from models, but a direct spectroscopic measurement of specific molecules in a specific atmosphere on a specific other world. For the first time in history, the question of whether we are alone in the universe ceases to be philosophical. It becomes an experimental, testable, measurable instrument that is being built right now in the Chilean desert. The ELT is not the only very large telescope on the horizon, but it is the largest, and that makes a difference. The Giant Magellan Telescope EMT is being built at the Las Campanas Observatory in Chile with an equivalent aperture of 24.5 meters, 7 mirrors, each 8.4 meters in diameter, several of which have already been polished at the Richard Karras Mirror Laboratory at the University of Arizona. The 30-meter astrometer telescope, TMT, was planned for Mauna Kea in Hawaii, but protests from native Hawaiian communities who consider the mountain sacred delayed the project for years. And by 2025, a final construction site had not yet been determined. The astronomical community views all 3 instruments as complementary, each with its own unique capabilities and instrumental suite, but the physics of the aperture leaves no ambiguity. The ELT, with the AOSI diameter of 39.3 meters, collects 2.6 times more light than the GMT and 1.7 times more than the TMT, and for the task of spectroscopy of the atmospheres of rocky planets, it is precisely this advantage that proves decisive. This mountain, this telescope, this mirror, they're not being built to set a Guinness World Record, but to solve a specific scientific problem that no previous instrument could solve. The ELT project is the brainchild of the European Southern Observatory, an intergovernmental organization comprising 16 member states: Austria, Belgium, the Czech Republic, Denmark, Finland, France, Germany, Ireland, Italy, the Netherlands, Poland, Portugal, Spain, Sweden, Switzerland, and the United Kingdom, with Australia as a strategic partner since 2017. ESO was founded in 1962 by 5 member states with the shared vision that European astronomy needed a shared infrastructure to support observations in the southern celestial hemisphere, which was inaccessible from European territory. ESO's first major observatory, La Silla, opened in Chile in 1969, followed by Paranal with the Very Large Telescope, VLT, in 1998, and the ALMA Millimeter Wave Observatory in 2013. The ELT is the third generation of ESO's flagship project and is larger in scale than any previous one, with a total construction cost estimated at approximately 1.3 billion euros. For context, the James Webb Space Telescope cost about $10 billion, meaning the ELT cost about 8 times less, while collecting 36 times more light. The difference in cost is explained fundamentally. A ground-based telescope does not require a rocket launch, operation in zero-gravity conditions, an autonomous power supply, or a complex communication system spanning millions of kilometers. The ground-based telescope can be repaired, maintained, and upgraded. Each of the 798 segments can be removed, transported to a workshop, reground, and returned to its place. Webb is beyond repair. It is located 1.5 million kilometers from Earth at the L2 Lagrange point, out of reach of any manned mission with current technology. The ELT will operate for decades, perhaps half a century, accumulating data to a volume that no single space mission could possibly cover because it simply doesn't have the time. 4 ELT scientific instruments are under development simultaneously in several European countries, each the product of years of engineering work by teams of dozens of scientists and designers. Harmony, high angular resolution, monolithic optical and near-infrared integral field spectrograph. ANGURSH is the main instrument. It will perform high-resolution spectroscopy by breaking down light from the atmospheres of exoplanets and individual stars in distant galaxies into chemical components. Mikado, the multi-AO imaging camera for deep observations. It will produce direct images with angular resolution never before achieved from Earth's surface. One of its main targets is the center of the galaxy, where stars orbit the black hole SGRA star at speeds of a few percent of the speed of light, and Mikado will track their orbits in detail, inaccessible to any existing telescope. METIS, the mid-infrared ELT, Ishanitam imager in a parachute Brownian and spectrograph, will operate at mid-infrared wavelengths, penetrating dust clouds in star-forming regions and directly simultaneously imaging the thermal radiation emitted by the surfaces of rocky planets in nearby star systems. Mosaic, the multi-object spectrograph, will simultaneously observe hundreds of distant galaxies, mapping the large-scale structure of the universe with statistical power never before achieved by any instrument. Each of these instruments represents an engineering project in its own right, costing hundreds of millions of euros, and all of them must be ready by the time the telescope sees first light. There is something that is difficult to express in press releases and technical articles. For 400 years, since Galileo Galilei pointed a lens at the sky in 1609 and saw moons orbiting Jupiter rather than Earth, each new telescope has displaced humanity from what it considered a privileged position. We are not at the center of the solar system. Our system is not at the center of the galaxy. Our galaxy is not at the center of the universe. The universe has no center at all. Each shift was met with resistance, and each was eventually accepted, slowly changing who we consider ourselves to be within the scale of this space. ELT opens the next shift if it detects biosignatures, oxygen, water vapor, methane in the right combination in the atmosphere of a planet orbiting in the habitable zone of another star. The universe will not be empty. Life, then, is not a coincidence, not a single anomaly on one pale blue dot in an unremarkable corner of an average galaxy out of 200 billion that exist. Life, then, is a phenomenon, perhaps ordinary, perhaps as natural as the fusion of hydrogen into helium in the depths of stars, a process that occurs in every star, in every galaxy, without exception. This revision, if it comes, will be the biggest shift in humanity's sense of itself. Since the publication of Copernicus's 1e Revolutionibus 2-18 Orbium could end up in Class A, in 1543, the highest level of the new class. And I stand size and fighting it could come from a mountain in the Atacama Desert, from a mirror 39.3 meters in diameter, from data collected on some ordinary night in 2031. It is now 2025. ELT is 3 years away from first light. 3 years, and this instrument will begin to look where no human device before it could look with sufficient acuity. We already know where to look. We already know what to look for. We just need to wait for the machine that can find it, and it's being built right now. Under ideal conditions, the system will be able to correct the atmosphere with a resolution of approximately 0.004 arcseconds. This will allow the coin to be distinguished from a distance of 200 kilometers due to powerful optics and a large mirror. At the Cerro Armazón Zaarch construction site, the pace of work is accelerating. Their dome has been installed. The segments are being assembled. Each of the 798 segments will be marked and checked carefully before final placement in the structure. But the final alignment will only occur after first light, when the system is ready for operation. The ELT's first light is scheduled for 2028, a date that cannot be missed according to ESO's plan. The history of telescopes is a history of displacements when humanity descended from its revered heights. In January 1610, Galileo saw the moons of Jupiter not revolving around the Earth. Geocentrism was broken. In 1781, Herschel discovered Uranus and expanded the boundaries of the known world twofold. In 1924, Hubble showed that Andromeda is a separate galaxy. The number of stars has grown exponentially. In 2023, the JWST discovered galaxies so close to the Big Bang that models could not explain them. But all these discoveries concern stars and space. Which by definition are scientifically far removed from life on Earth. ELT will change its focus. It will look to where life might be, where a new home for humanity might be. The first weeks of work will be spent on calibration, stars, clusters, and checking the telescope's spectral instruments. By the end of the first month, the Science Council team plans to point the telescope at TRAPPIST-1. The system was not chosen by chance. The star is bright, 3 planets are in the habitable zone in the same orbital plane. The first observation of TRAPPIST-1I is planned for the 3rd month of operation at 90% system performance. It would take about 40 hours of light integration to produce a spectrum sufficient to detect oxygen in the atmosphere. 40 hours of observations is approximately 40 million euros of computer time on an instrument of this class. This is one of the most important observational programs in the history of astronomy in all times of scientific research. ESEIO plans to have all spectral instruments ready by July 2028, in time for first light. This is a promise to do real science literally in the first weeks of the instrument's existence after its introduction. There is a real race between ELT, TMT, and GMT, despite the official complementarity of the instruments. TMT hopes for first light in 2029, subject to the resolution of a long-running dispute over the construction site. GMT is ready for installation and plans for first light in late 2029 or early 2030 at Las Campanas. ELT has an undeniable advantage. The dome is already in place, the foundations are poured, and the optics are being installed actively. First light is scheduled for 2028. This is the physical schedule of the project, not a paper promise. In April 2028, NASA plans to launch the Roman telescope to search for planets using microlensing. Roman will work with a different method that complements ELT rather than competes with it in spectroscopy. In the lead up to first light, the global community can expect breakthroughs in the analysis of JWST's archival data. Some team of astronomers may announce the detection of biosignatures in the spectrum of the planet TRAPPIST-1. The spectrum can reveal oxygen, carbon dioxide, and water vapor in an interesting combination of molecules. Such an announcement would seem impossible. Webb should not have picked up such a weak and subtle signal. Critics will point to geochemical processes and volcanism as possible sources of such a picture. When the community splits into disputing parties, ELT will be able to use its power to finally resolve the issue. The night of first light on Cerro Armazones will begin, like all nights on this mountain: cold, wind, stars. A team of engineers, astronomers, specialists, and journalists will gather at the control site. The ESO director may give a speech about the relevance of the moment to the greatest events in science. The robot will deploy a protective screen, and the mirror will open to the night sky for the first time at a historic moment. Everything should work completely silently, thanks to electronics and hydraulics, without mechanical sounds. The first light might come from Alpha Centauri or another bright guide star nearby. The monitors should display a perfect image, a sharp point without a halo of blur or noise. There will be sighs of relief in the room, applause, then silence as people take in the moment. The machine can work perfectly, just as the engineers had calculated in their many years of project calculations. First light calibration will take several days: stars, clusters, spectral sources, and tests. Each test must confirm there are no errors, the calculations are correct, the telescope is working as a coherent whole. Once the ELT is declared ready, the team will be able to send it to its first galactic targets. Observations may reveal structure hidden by blurriness in all previous astronomy instruments. The first result could be published in Nature, the first scientific discovery of ELT in hundreds to come. 2 weeks after first light, a team of astronomers plans to point the ELT at TRAPPIST-1. Conditions must be ideal. The atmosphere is stable, there are no clouds, and the adaptive optics are working properly. TRAPPIST-1's first transit will take 4 hours, with the planet passing in front of the star's disk. The data will be received in real time. Water vapor can be clearly detected, carbon dioxide too. Oxygen may be at the edge of detection and will require further observations to confirm. Several more observations of TRAPPIST-1e are planned for the night, accumulating the signal in the spectra. By morning, the team may have data. Water and carbon dioxide have been detected with sufficient certainty. Oxygen may be finally confirmed in the spectrum over the next few weeks under better conditions. An article submitted to Nature can be approved without comment. The significance of the result is obvious. If Nature publishes a paper about the detection of biosignatures in TRAPPIST-1e, it will make history. This day may go down in history as the day of the first discovery of a world with an atmosphere around another star. Such an atmosphere may contain molecules synthesized by life on Earth. The news will spread as an event that could rewrite humanity's understanding of the universe entirely. Within 24 hours, more than 1 billion posts could appear on social media about a discovery of this magnitude. Within 48 hours, presidents and prime ministers will make official statements about the significance of the event. World media will be running special editions and interviewing astronomers from all over the world for a week. The Pope may reflect that the discovery does not contradict divine creation. The scientific community will likely remain cautious in its interpretations and possible conclusions from the data. Oxygen can be produced by photolysis of water without biological life. This is a known process. This is abiogenic oxygen, and models show that such quantities are quite possible on a young planet. Methane, which usually indicates biological activity, may not be detected in the spectrum at all. Ozone may also not be clearly visible, although its presence would indicate a biological origin. The answer will most likely not be, yes, there is life there, but the signs are interpretable as a possibility. This will be enough to split the world into supporters and skeptics of the biological version. The debate will unfold in magazines, networks, offices, but the era of uncertainty will end after that. We will stop asking, is there life beyond Earth, with spectroscopic information about worlds? ELT observations in the early years may focus particularly intensely on the TRAPPIST-1 system. All 3 habitable zone planets are planned to be observed dozens of times, each adding detail. TRAPPIST. 1F may show a strange spectrum. Ozone is clearly visible, oxygen is abundant, and methane is absent. It would be as if the planet were caught between abiogenic oxygen and a completely biological atmosphere. TRAPPIST-1G may show a different picture, a thick atmosphere, clouds, hints of organic chemistry. Articles may be published monthly, each adding to the portrait of 3 stages of potential life development. GMT is expected to reach first light in late 2029 and focus on other observing targets. TMT will continue to delay the first light due to unresolved disputes over the location and geography of the construction. ELT may remain the undisputed queen of the sky for habitable zone planets for years to come. The discovery of potential biosignatures could occur at a time of deep crisis on Earth. The era is already marked by a wave of climate disasters. Floods, droughts, and fires are reaching their peaks. Many people feel despair about the future of the species as ecosystems degrade at an alarming rate. And at such a moment, ELT can deliver news that can rewrite people's psychological paradigm. We can learn that we are not alone. There are other worlds where there may be life in a potential home. Life may turn out to be the norm, the result of physical laws, and not a rare and unique miracle. Or an idea based on spectroscopic data from a mountain in Chile could change the cultural conversation. Proxima Centauri b will be one of the priority targets for study in the ELT observation program. Proxima b may not have an atmosphere. Superflares could have erased it over billions of years of stellar life. LHS-114 OB may show an atmosphere quite unexpected, hydrocarbons, but no obvious signs of life. However, a detailed analysis can reveal water on the surface and organic compounds of complex chemistry. Not life, but a path to life, a prebiotic world where chemistry can form molecules for life. Kepler 442b is planned to be observed after a year of data accumulation due to the weakness of the star's signal. If ELT collects enough data, water and oxygen may be detected in Earth-like quantities. Whether there will be life there may remain an open question, but the data will be real and scientifically measurable. In its first 3 years of operation, ELT can observe 200 systems and obtain spectra of 50 worlds. 12 may show combinations of substances sufficient to be considered potentially habitable. 2 systems, TRAPPIST-1e and K218, will potentially show signs of biosignatures in their atmospheric spectra. Will this be proof of life? No, it's just that the chemical state is associated with life on Earth. But this may be enough to give the question, are we alone, an empirical answer. By the end of the first years of work, astronomers will be able to issue a joint statement, such as the Cerro Armazzoni's Memorandum. Thousands of astronomers will be able to claim that spectroscopy has revealed atmospheres with signs of life. Conditions for life may not be unique to Earth, but are potentially widespread throughout the universe. This will turn the ancient question from a philosophical level to an empirical and scientifically measurable one. Such a document could become the official position of the scientific community on life beyond our planet. It will be cited at the UN, discussed in parliaments, and taught in schools as part of science. In the coming years, ELT's work may continue to expand across the observable sky. Stars in the immediate vicinity of the Sun, at distances less than 50 light-years, will be a priority, because it is precisely in the vicinity of the Sun that there remains hope of discovering life on nearby accessible worlds. Each new exoplanet in the habitable zone will be able to undergo spectroscopic analysis in detail. The ELT can resolve details that astronomers dreamed of just 10 years ago. By the end of its first years of operation, the telescope will be able to observe more than 300 systems with habitable planets. Of this number, some may show combinations in the spectra that are worthy of attention as biosignatures. The scientific community will likely develop a new classification for potential biosignaling systems. Class A, pure biosignatures, probability of life greater than 70% based on current scientific observations. Class B, possible biosignatures, 30 to 70% probability, requiring further spectral analysis. Class C, weak indicators that can be explained by abiogenic processes without life. TRAPPIST-1e and K 2-18 could end up in Class A, the highest level of the new classification. Proxima b will receive constant attention, but the results may show no atmosphere. Studies of Proxima b will help understand the role of stellar activity in the loss of planetary atmospheres. Models of exoplanet evolution based on ELT data will begin to be completely revised. Red dwarfs may prove to be cruel for crueler fustat. Had say chicks is dates a suthen som saying mum profaskisi causing.
Maxine had say Barma store garate and see Yodia and said that Sophia chamber to pensions.
Paradoxically, this would mean that life on quiet red dwarfs, if it arose, could be stable. LH, S114, O, B, and several similar systems may exhibit prebiotic chemistry closest to life. They will allow scientists to study bridges between non-living and living chemistry in the real worlds of other stars. Instead of experiments in the laboratory, astronomers will be able to observe natural experiments in space. When Greenwich Mean Time becomes fully operational, it will add a second perspective to the same observing systems. GNMT will add a new perspective on the same systems, but with a different tool for studying. Synthesizing ELT and GMT data will enable spectroscopy with unprecedented resolution and accuracy. The combined observations of the two telescopes can provide a picture that would be impossible for either telescope alone. TMT may finally begin construction in the early 2030s in southern Spain. First light of TMT may be scheduled for 2035 to 2036, when ELT and GMT will already be in full effect. But by that time, major discoveries in exoplanetary spectroscopy may already have been made. History will remember the ELT as the telescope that first attempted to answer humanity's oldest question. Over time, the international community may hold major conferences on the results of ELT. Astrobiologists, physicists, philosophers, theologians, and politicians from all over the world may attend. Observational results from a variety of systems and potential Class A candidates will be presented. A consensus can be reached. Life is not a rarity in the universe, but rather a norm of physical laws. Even if only a few systems in the immediate vicinity show signs of life, statistics suggest billions. This could fundamentally change the paradigm. We are not an exception, but part of a universal phenomenon. The Pope may issue a statement that the discovery of life outside Earth does not contradict faith. Moreover, it can expand the understanding of divine creation and the greatness of the Creator infinitely. Atheistic associations can also speak out, recognizing life as the result of natural laws. Political leaders will raise the question of how humanity should respond to the discovery. A new platform for discussion will emerge: the ethics of contact, the rules of interaction with potential life. Should we send signals towards Class A systems, or is this potentially dangerous? Could potential microbial life on other worlds be compatible with Earth's biochemistry? Is the discovery of life outside Earth sufficient grounds for a philosophical revolution in civilization? An international organization may be founded to protect potential extraterrestrial life on planets. Its mandate could include coordinating telescope observations and advocating for potential life, and the development of protocols for interaction with extraterrestrial biology if such contact occurs. ELT operations, starting with first light in 2028, could culminate by the mid-2030s. The telescope will be able to observe more than 1,000 systems, some of which may show potential biosignatures. Direct spectroscopy of atmospheres, impossible for Hubble and difficult for Webb, may become routine. The level of detail will make it possible to distinguish not just the presence of oxygen, but its concentration by latitude. It will be possible to track how atmospheric circulation transports biological gases across the planet's surface. It will be like decoding the global life cycle of another world in real time. ELT. Engineers can achieve everything planned and even exceed the most optimistic forecasts. Future ceremonies in Chile may mark anniversaries of the first ELT light as a turning point. Speakers may speak of this instrument as a turning point in human history. The director of ESO might say, "We built a machine to look at the stars, and we can see life. This machine has the potential to change not just science, but the meaning of who we think we are and where we stand." We will cease to be a civilization searching alone in the void, hoping for an answer from nowhere. We can become a civilization that has found the answer, and that answer will sound like the hum of a million voices of life. A memorial plaque to the creators is planned to be installed in the museum at the observatory on Cerro Armazones. It will be engraved with the names of all the engineers who worked on the ELT and their countries of origin. The role of the European Southern Observatory which brings together the capabilities of 16 countries, will be particularly noted, and it allowed these countries to build a machine capable of rewriting the understanding of place in the universe. ELT's work could continue for decades, adding spectra to the archive of knowledge about life every night. The question, are we alone, may be answered, but a new, even deeper question will arise. If life is widespread, where exactly is it found? What do all the living worlds in the galaxy have in common? Are there universal principles that connect life on Earth with potential life on TRAPPIST-1e? Thank you for being with us on a journey that could rewrite our understanding of the universe entirely. Every view, every shared video, every comment helps others know about it. Your curiosity is the fuel that can drive science forward in its search for the truth about life. Until next time, when we explore the next great question in science and space, life on other worlds may no longer be the subject of science fiction novels or religious speculation. This could become a physical fact recorded by direct measurements from a telescope in the Chilean desert. When people in the future study the history of this period, they will be able to see the turning point of civilization. Until 2028, humanity asked if we were alone, and there was no answer, only hopes and fears. After 2028, we may learn that there are other worlds where conditions for life exist and are possible. This knowledge has the potential to change the psychology of humanity at the most fundamental, deepest level. Depression associated with cosmic loneliness can be replaced by an awareness of the universality of life. Hope, a rare commodity for a civilization on the brink of environmental crisis, may be founded. If life is natural and widespread throughout the universe, then perhaps we too have a future ahead of us. Maybe our civilization is not the only one, and there is someone to learn from, and somewhere to go to develop. Perhaps the universality of life means the universality of some principles of its development in the universe. And if this is so, then our knowledge will not be limited to the terrestrial biology of a single planet. We will be able to search for principles that can unite life on all worlds where it has ever arisen. New disciplines may emerge in universities: astrobiology, biosis, exoplanet spectroscopy, homebodies, life biology. Young scientists can choose specialties motivated by ELT discoveries of recent years. They will want to understand what the general chemistry of life is, if life is truly universal across the galaxy. What is the minimum complexity of chemistry required for life to arise from non-living matter? Why carbon, the basis of all life on Earth, might also show up in the spectra of other worlds. Answers to these questions may emerge over the next decades of work by ELT and its successors, because the work of a telescope only begins at first light and does not end there. In the first years of full operation, ELT may prove its power and reliability as a scientific tool, but this will only be preliminary reconnaissance in space, only the first steps in a large new land. Observations of more distant systems, dimmer stars, and more complex atmospheric spectra lie ahead. Ahead lie instrument upgrade modules, new receivers, and higher-end spectrographs. Hundreds of thousands of nights of observation lie ahead, each adding a brick to the vast edifice of knowledge. Ahead lies the potential discovery of true biosignatures, not just hints, but definitive proof. Because the first ELT data will only be hints, indications of the possibility of life on the worlds. True proof may come when a chemical imbalance is discovered that is impossible without life. Ozone, in an atmosphere with oxygen, but without methane, is already suspected of being of biological origin. But ozone plus nitric oxide plus a few molecules in a non-equilibrium state is almost a certainty. The ELT can gradually approach this level of detail in its spectroscopic measurements. A few more years of full-fledged work and humanity may receive not just hope, but a measured fact. Not a guess, but proof of the presence of living organisms on planets around other stars in the galaxy. It will be a moment so great that all people living at that time will remember it for the rest of their lives. How do people remember the day humanity first walked on the moon, or the day the internet became available? The moment we learn about possible microbial life on TRAPPIST-1 FIT may be comparable to that day. Because this will be the moment when we will know for sure we are not alone. Life is not a rare miracle in the universe. Currently, the ELT stands on a mountaintop in the Chilean desert, undergoing final installation of all systems. Its 39.3 meter diameter mirror will soon begin collecting light traveling through the void of space. Photons born in stars will pass through the atmospheres of potentially living worlds on their way to us, and they will be fed into spectrographs, which will break the light down into its components for chemical analysis of the atmosphere. Chemical analysis of light is like breathing on a mirror and seeing the fingerprints of life in the spectra. And these fingerprints may become visible in ELT data in the first years of its scientific observations of the night sky. Life can leave its traces in the spectrum of light that comes to us from hundreds of light years away, and then humanity will be able to read them thanks to the machine that we have been building for many years in Chile. Thank you for joining us in this story about a telescope that could open up a new world for us. Thank you for your curiosity, your attention, your belief in the importance of fundamental science for us all. Subscribe to the channel to stay updated on future discoveries in astronomy and telescope development. And remember, each of you can become the star that lights the way for the next generation of scientists. Until next time, in the vastness of space and in the depths of the unknown in our universe.